you prove that if I have 3 particles, 1, 2, 3, yeah, very good. So now there are 3 particles, let's say their momenta are P1, P2, P3, and you can even take them to be massless if that's more convenient for you. So we know that at every vertex energy momentum is conserved, right? So I have assumed arrows like this. For me, time always moves this way. Some people draw Feynman diagrams with time moving upwards, so this is always implicit for us. This is the time axis. So P1 plus P2 equals P3. Now you square both sides and you can see that. Let's square both sides. So this is m1 squared plus m2 squared. I have assumed that these two are on shell, right? Plus 2p1 dot p2 is equal to, let us say, I'll put it like this. Okay. So if I say that this is 0, this is 2 E1 E2 minus 2 P1 dot P2. So as the energy and momentum of these two particles changes, including the angle between them because it's a dot product, this so-called mass keeps changing, right? And therefore this is not a fixed quantity, and therefore this object is not on shell. So now you could have asked the question, suppose I know that P1 and P3 are on shell. Then what would I do? I would write this equation as P1 minus P3 squared is equal to minus P2 squared, right? So I know that this is m1 squared, I know that this is m3 squared, minus I have the same problem, right? P1 dot P3 is equal to, so if I know that P1 and P3 are on shell, then of course m2 becomes a variable quantity, and therefore this will not be on shell. So any 2 can be on shell. Of course 2 can be off shell. All 3 can be off shell. There is no constraint on that, right? But as far as we are concerned, if 2 are on shell, the third cannot be on shell. That is really the statement we are making. Okay, and in electrodynamics we have only a 2-point vertex. So if I have a vertex which looks like this, then this is a 3-point vertex. These are external lines. These are the particles which are interacting, they are on shell. These are the external particles which we are detecting, so they are on shell, which means that at these two vertices, this object in between from mu to nu is off shell. Suppose I even write more complicated diagrams like this. I mean, I am not telling you whether this is a photon or a fermion or whatever. I mean, I can keep doing things like this, right? Now you can see that there's a bit in between here. Sorry, this is off shell, but this is also off shell, and maybe this is also off shell. So all 3 can be off shell. Is this clear? Is this clear? So there's no restriction on the number being off shell, but what we always say is that external particles, so these are free particles, external particles are always on shell, and the detected particles are always on shell. With that constraint, every other combination is allowed. Is this clear?
Yes, ma'am. Ma'am, what reason you told about why we cannot have 3 electron means at the vertex means we must have 2 electron and 1 photon. Why we?
Why it is not why? See, this is standard model. Standard model is written down by observation. Yeah, no, I mean, you can, there are many reasons. So it depends on the theory. So I am keeping in my mind some model, even though I have only spinless electrons here, I am keeping in my mind some model which is going to reflect the real world. Okay. So in that real world, yeah, so in the particular case, I can have 4 electrons in that case, you see. So I could have had a vertex, yeah, 3 electrons will not work, but I could have had 4 electrons, I can conserve charge. But the thing is that such an interaction vertex gives rise to physical consequences which is not observed in nature. So in phenomena, so okay, by the way, what we are now doing is called particle physics phenomenology, okay. So as the name implies, you observe the phenomena and then you write a model for it. So it's called standard model. It's not a theory, it's a model. So we are writing the standard model of particle physics. So it's usually called SM. Okay, and this is simply by observation. So it's a model. You have to be able to explain the phenomena that you see in nature. Okay, now as you said, 3 electrons cannot come and interact at a point because of charge conservation, but 4 could have, but this you do not see. Okay, so you have to eliminate it. So the way you eliminate it is then you invoke certain symmetry principles, and that is your symmetry group, which in the case of electromagnetism turns out to be the U1 group. And then we will come to it in maybe another 10 lectures. What we say is that if we demand that the Lagrangian has a certain special invariance, which we will discuss, maybe we are going too far away, which is called local invariance under this group, then it will describe all the possible interactions of the particles in the model with the mediator. Okay? So if I invoke U1, the only interaction I get is this, the electron or muon or some charged particle with the mu field, the electromagnetic field. The electromagnetism theory is very, very simple and has only one vertex. That is why it's a nice thing to start out with. So it's a major relief that I have only one type of vertex, and therefore I don't have too much complexity. Is this clear? So now what I am going to do is that, if this is clear, I'll move on. I wanted to do 2 things today. Yeah. What I want to do today is, yeah, please ask.
So, ma'am, when we studied about some process, so we draw some Feynman diagram.
Yes.
So in Feynman diagrams, we draw actually first order Feynman diagram.
Yes.
And all other orders, just like second order and third order, we neglect because of their amplitude is very low. So this kind of process in which we are talking about, in which three electron vertex cannot, it is completely discarded, or its amplitude is very low. So that's why we not use it.
It's a very nice question. So the statement again is that when we come to writing formal Lagrangians, which we will do in 10 classes from now, you will see that even at higher orders, you do not have the 4-point interaction vertex of electron with electron. So for example, here is one diagram. Here is my E mu going to E mu. And this is what I said is called the tree level lowest order diagram. Any higher order diagram, for example, since this question has come up, okay, this is the basic diagram. I have to add some higher order term to it. What can I do? I can add either another electron or a muon, or I can add a photon, right? So how do I add suppose I want to add an electron. Where can I add an electron? Actually nowhere, you think about it. Okay, where can I add a photon? I cannot add a photon on a photon because photon has no charge. Photon is the mediator of quantum electrodynamics. It can only interact with charged particles. So the only place I can put a photon is here, or I can put a photon. I mean, I'm just making an electron in muon line. Okay, so it could have been on the muon line. Okay, and if I go to even higher orders, I will get what are called.
These photons are escaping.
Yeah, these photons are escaping. Okay, and if I go to even higher orders, I will get what you call a loop diagram. The photon is emitted and absorbed and not observed. So you can see that I can have a diagram like this. I mean, I'm not going to write all the diagrams, just for you to understand. I can also have an exchange like this. Okay, so here I have added a virtual photon, and here I have added a real photon. Okay. Now, of course, you can argue that, let me just finish the statement, then you can ask your question. So, you can argue that this is no longer E mu goes to E mu, this is E mu goes to E mu gamma. Okay. But however, this is still E mu goes to E mu because the photon was emitted and absorbed. So these kind of contributions become the higher order corrections to these diagrams, and you will actually compute them in quantum field theory course, and I can tell you what the answer to this contribution to this cross section is infinity. So to make sense out of this higher order term, on one hand you are saying that this was tree level diagram is proportional to E squared, and therefore the matrix element squared is proportional to E power 4. This diagram is matrix element is proportional to E power 4. Since E squared is proportional to alpha, which is 1 by 137, this contribution must have been smaller than this contribution, only then perturbation theory has a meaning. But because of certain complexities associated with virtual corrections, this diagram turns out to be infinite, and how these infinite contributions are reabsorbed and the quantities redefined such that this contribution actually becomes smaller than this contribution is the whole sum and substance of quantum field theory. We will not look at any such diagrams in this course. Okay? Now ask the questions that you have.
I was just saying that the real photon does not correspond to the dynamics we are studying.
Yes, exactly. It is a different process, but there is a subtlety here, and you will remember this when you do this in the quantum field theory course. It's possible that this energy momentum of this photon is so small that it kind of looks like an E mu goes to E mu process. Okay, and some very nice things happen, and you can learn about it in the field theory course. Okay, so actually both the contributions will be there. This virtual contribution and this real contribution when the photon momentum is very soft, very low. Okay, so there is a soft real photon and a virtual photon contribution, and they add in certain surprising ways, and they enable you to get a nice finite well behaved answer. So I am not going to say anything more than this. This is not part of my course. We will come back to phenomenology. Phenomenology is very simple. So we wrote down this diagram. I am coming back to E gamma goes to E gamma, and the matrix element, let me call this vertex mu, let me call this vertex nu, and this we wrote as the vertex factor at mu times the propagator of the photon from mu to nu times the vertex factor at nu. So for those who don't remember, so I q, so let's call it A, C, B, D. So this will be PC plus PA mu, and then we had a minus I G mu nu by Q squared, where Q was the momentum of the photon, and then we have I Q PD plus PB. Sorry. Okay, and so we wrote down this, we can write this by inspection by writing down a vertex factor like this as I Q, where Q is the charge. So let's call this I and F, PF plus PI mu. And then we wrote down the photon propagator from mu to nu with a momentum Q as minus I G mu nu by Q squared. Okay, so what I wanted to tell you in this class, as I said, I will solve for you classical Green's function for classical electrodynamics, and then I will relate it to what we call the propagator here. This is due to Feynman, so this is called the Feynman propagator. So this will be derived for you exactly in the field theory course, but so that you can understand what is propagating and why, I want to give you the analogy with electrodynamics which you have already done before. So let me set up the problem. So please remember that we have set up the Feynman rules, we have solved for the transition matrix element squared, we have defined the cross section, and we have yet to simplify it. We have to write down these Feynman rules, we have to write down the matrix element, square it, simplify it, and get the cross section for E mu goes to E mu when there is no spin, only charge. We have set that problem aside and we are now concentrating on what you call the propagator, for which I will start out with what do you mean by Green's function in classical electromagnetism. So we come back to our favorite equation, which is box A mu is equal to J mu. Okay. Now there's always going to be problems with units in electrodynamics. Let me write down, so the equations explicitly. I have 1 by c squared d squared phi by dt squared minus del squared phi is equal to, now this is due to CGS units. No, I think it comes the other way. Okay. To get the wave equation from Maxwell's equations, your MKS units of, for example, del dot E. Okay, this is extremely complicated. So we go back usually to CGS units. So this 4 pi need not trouble you. It just comes from writing. Instead, I am writing CGS units 4 pi. So those of you who are, I think all of you are used to MKS now. CGS is just convenient, and that's exactly the 4 pi rho that you get over here. Okay. In general, all I need to say is that my A mu, which is any term of A mu, satisfies a generic equation, let us call it psi, right. So this is my starting point. Which other part of the board?
The right hand side.
Is it better here?
Yes, ma'am. I mean, once you have written on one part, instead of erasing, you could erase over.
Oh no, because I have a derivation and I want both halves. So, but that's why I removed it. Okay. Yeah. I'll do that next time. I mean, it's not important because this is my starting point. So if you want, I can just start over here. So this is a differential equation, and we know how to solve a differential equation. So I hope, by the way, you know this equation, right? I mean, you know how to get this equation, right? You start out with,
Yes, ma'am.
I mean, you start out with d mu, f mu nu is equal to j nu and stuff like that, and then you put in the gauge condition. Everyone knows that, right?
Yeah.
Everyone has seen that. So you put in the gauge condition. Oh, who said no? Can you say again so that I can see? Okay. Okay, fine. So have you seen Maxwell's equations in this form?
Yes, ma'am, I have seen them, but we didn't solve it like in
Okay, fine. Okay, let me, it makes no sense to continue until this is clear. So sorry, I'm going to start out here, okay? So I think there should be a 4 pi here, but I'm not going to care too much about it. This equation you have seen? Jatin?
Yes, ma'am.
Okay, fine. And you know what f mu nu is?
Yes, it is the
D mu A nu minus A mu B nu.
Okay, you know this, right? This is all right?
yes.
Lot of people are missing today. 1, 2, 3, 4, 5, 6, 7, 8, 9. No. Koina is missing, is it? Okay. Okay, fine. So you know this equation, right? So now I'm going to substitute over here. So I get d mu A nu minus d nu A mu is equal to 4 pi j nu. Now what is d mu? This is box, right? D mu is what we call box, right?
Yes, ma'am.
Yeah. Minus, now you see this is a derivative operator, this is also a derivative operator, and they commute. So I can interchange the order of this and write d nu times d mu a mu is equal to 4 pi j. Okay. Now I will choose a gauge and I will explain that in a moment, where d mu a mu equal to 0. Then my equation becomes box a nu is equal to j nu. If you remember, I wrote it as box a mu equals j mu. This is the equation that we used to solve for A when we derived the transition probability amplitude for Klein-Gordon equation interacting with electromagnetic field. The solution we wrote was A was minus 1 by q squared j fi, right? Yeah, so this is the beginning, this is the starting point, and this is the important thing. I have chosen a gauge, this is called the Lorentz covariant gauge. This is a Lorentz gauge, and in the homogeneous case, what is the homogeneous case? No external currents or charges, right? I have box A nu is equal to 0, and if you want me to write it down, this is exactly, I have got this equation here, so I have dropped the 4 pi's everywhere. So box is 1 by c squared d squared A nu by d. I hear something. Is equal to j nu or 0, and when RHS equals 0, A nu is equal to A nu 0 e to the minus I whatever k dot x, right. So I have a wave, this is the wave equation because the solution is a wave. So this is a wave whether it is in A0 which is phi,
When the K and X are also 4 vectors.
yeah, k and x are 4 vectors. If you want, I can write it as, okay. So we are not yet done over here, we are not yet finished because the solution is not in A's are potentials which are not directly observable. What are observable are the E and B fields, right. So we have to actually get the wave equation in terms of E and B fields. There is simply one more step, you can do it yourself, okay. I am not going to do it, but basically what I want to highlight for you is this quantity. We have already assumed a gauge and that gauge takes us in the following direction. So you can, I hope you know that B is equal to del cross A, E is equal to minus del phi minus 1 by C dA by dt. See, by the way, even though I keep dropping 4 pi's and c's everywhere, time and space have the same dimension. Del is d by dx. So therefore, this should come as c dt because c dt is also a d by dx. It's a distance. So that's how you remember how to put back the c's, okay. And if I put it back wrong, please tell me or you correct it yourself. So this is the equation for the E and B field. You can go back and actually write the solution in terms of the E and B fields if you wish. You will again get a wave equation. So you will in fact again get E is equal to E0 e to the minus I k dot x, and similarly B is equal to, so you can keep solving like that, but we are not interested in that. We have a wave and this is the inhomogeneous solution when there is a source term. Source term is that j nu is equal to rho comma j. So either j by c or so maybe j by c. I am not going to guarantee the c's, okay, fine. And if you put it in MKS, then you will get c squared is equal to 1 by epsilon naught mu naught, right?
Ma'am,
Yeah.
ma'am, we choose gauge as a.
I am just going to come to gauge, yeah, that's what I am just getting rid of all the other definitions because I realize I went backwards, so I just make sure I define everything over here, and I think I have now done that. So what I want you to observe is this, well, let me finish this comment. B and E are related to derivatives of the potentials. They are not related to the potentials themselves, and this is why the gauge choice is available to you. Now ask a question and I will proceed. I am going to talk more about the gauge.
Yes, ma'am, I was asking the way final solution you write E is equal to E naught E raised to power. E is again a 4 vector.
No, this is the electric and magnetic fields.
Contains-
These are the electric and magnetic
So
fields.
it contains.
This is the
both
3
electric and
vector.
magnetic.
No, you get B is equal to also, I mean I didn't write B0 e to the minus I k dot x, okay, and you will get E cross B is equal to 0. All those solutions you will get. There is nothing new. This is electrodynamics written in new packaging, old wine in new bottle, that's all. Okay, so the same solutions that you get from writing Maxwell's equations in 3 vector notation you are going to get now. Nothing is different. Please understand that E and B cannot be written as 4 vectors. E and B are components of the 6 dimensional here, 6 dimensional F mu nu, right? F mu nu is totally antisymmetric. F mu nu has F0i contains the E fields and Fij contains the B fields, right? I hope you know that.
Yes.
You can write F0,
Yes.
F01 is minus E1, F02 is minus E2, and then the column vector is plus, and then the others you can figure out. I don't remember that much of it myself. You can work it out, right? From this definition and from this definition you can immediately work out what elements give you what quantities, right? So all I am saying is that the homogeneous solutions, the homogeneous equation solves to a wave equation. That is why electromagnetic field is a wave, okay, and here you have omega is equal to k by c, yeah, k by c, okay. So if I write, I don't remember where the c goes, so we have k mu is equal to omega kind of ck, so I think I don't know where the k, c comes, okay. For me omega is equal to k, okay. It's a massless electromagnetic field, right? Fine, and therefore the velocity is defined as velocity, I think it's the other way around, forget it, whichever way. What will tell me?
Omega is Ck.
Omega is ck, no? Yeah, omega is ck, yeah, that's what it looks wrong over here. Omega is ck, yeah. So C is the ratio of omega, the energy to the wave vector, right? That is how you define, and that's how you get it to be this in MKS, right? So these are all your solutions. I am not worried about that. I want to make the remark about what you mean by this gauge choice. So I say that I have taken the gauge choice d mu a mu equal to 0. There are many other gauge choices you can take. What it means is that a mu is constrained. Not all components of a mu are free, because the 4 components of a mu have to satisfy this one constraint equation, okay. So suppose I make a mu transform to some a mu prime, okay, which is a mu minus d mu of some other new field lambda, such that box lambda is equal to 0. Now let us see what happens. When I do this, what happens to d mu of a mu prime is d mu of a mu minus d mu lambda, which is d mu a mu minus box lambda, but box lambda is 0, so this is, but d mu a mu was also 0. So the main thing is this, I have taken a gauge choice d mu a mu equal to 0. You see that when I make a transformation like this, d mu a mu prime is also 0. What is the significance of this transformation? You will see that when you substitute a mu goes to a mu minus d mu lambda, under this, so let me write it in words, under the transformation, these two transformation, E goes to E, B goes to B. Please check this, it's a 2-line thing. Just take, so vector A goes to vector A minus del of lambda, and A phi goes to phi prime, which is phi minus d by dt of phi, okay. Put that back here and find that E goes to E, B goes to B. So you say that the electromagnetic field, because what is the physical electromagnetic field? E and B vectors, right? That is the physical electric and magnetic field. They are invariant under this transformation. We are in fact coming very close to the U1 gauge symmetry, okay, but I am not going to go there yet. This is just completely classical at this point. Under this transformation, E and B fields remain invariant. Your gauge condition is also still satisfied. You can see the gauge condition is also satisfied, and it physically, we will see later why we need this condition is the following, that A mu has 4 components, A0, A1, A2, A3. But I want to then relate this A mu, and I will do it in quantum field theory, to the electromagnetic field. But the electromagnetic field, we know, is a transverse field, massless, and it has only 2 degrees of freedom because it has only 2 transverse polarization states. So from 4 degrees of freedom, I will reduce by putting these 2 conditions, this constraint and this subsidiary constraint, and I will get correctly 2 physical degrees of freedom, so that this A mu is actually going to be my electromagnetic field. As far as I am concerned, I have set this to 0 and I am starting out with box A nu is 4 pi j nu, and that is my starting point of this equation. Is this clear? So that was a quick review of electrodynamics, but we are still in classical electrodynamics. So all this now tells you that I can always choose so that this extra piece goes to 0. I can always choose so that my generic equation, whether for phi or whether for A, is going to be this equation which I represent as psi. Okay so far? Now I am going to take everything off because this is all not.
I have a question.
Yes sir.
Ma'am, we are choosing gauge because we can, ma'am, I am asking that because we are choosing gauge because we are unable to solve equation, or it is some sort of symmetry.
That's what I am saying, that right now I have shown you that, if I choose this gauge, okay, it is always valid because under this transformation d mu a mu prime is still 0, right. So it is a very consistent choice, but we will relate this gauge choice and the subsidiary gauge condition box lambda equal to 0 to the physical degrees of freedom of the quantum electromagnetic field. We will not do it now, we are anticipating it will come. Yeah, ask the question.
Box lambda is equal to 0 is also put by hand.
If you do not put box lambda by 0, then d mu a mu prime is no longer 0.
Yes, sir. So it is also put by hand.
It is not put by hand, it is a requirement for consistency. See, if I want to choose d mu a mu equal to 0, under this transformation a mu goes to a mu prime, which is a mu minus d mu lambda, E and B fields do not change, okay. So I am allowed to make this transformation because actually you know the reason why. You have always known it. We always know that a potential, if let us take only scalar potential, right. We know that the scalar potential, the 0 is arbitrary. I can always add some quantity to it, right. Only if potential difference has a physical meaning. This is a generalization of that. The fields are related to derivatives, right. Del cross del and d by dt. E is not related to A or phi, it is related to derivatives of A and phi. Similarly, B is related to derivatives of A and phi. So I can always add to A certain terms, this is the term, such that the physical E and B fields do not change. This is called a gauge transformation. But, and why is it called a gauge transformation? Because it is, I can add this at every space-time point x. For example, I can add d mu lambda 1 at point x1 and d mu lambda 2 at point x2. I can transform the A field differently at every different place, okay. Keep that in mind, we will discuss that also later further. But for the gauge condition to remain consistent, I need to apply the subsidiary condition, and therefore it becomes a requirement for the consistency of applying this gauge condition, okay. Is it clear? So here is our solution. So we have, this is how we solve electrodynamics and get back the old, as I said, get back the old answers, okay. But now I am not interested in solving the wave equation, I am interested in looking at the Green's function technique of solving this differential equation, and that will give us insight into our Feynman propagator in the absence of us knowing enough field theory to answer this question. So here is my solution. Let me start out. So we all know how to solve this inhomogeneous differential equation. I start out by writing the homogeneous differential equation. What is the homogeneous equation? Let me write. So now let me put in some notation. So what does this mean? This is my homogeneous differential equation. So what is psi going to be? Psi of x. By the way, this is, if you want I can put the t's, maybe actually I will put the t's because here it is important to see the t. On this side I have put the t's, okay. So psi of x is equal to integral d4 x prime g of x x prime f of x. So how do I know that this is the solution? Because I apply box on both sides. So what happens? I apply box. What does this mean? I am applying box of x, not box of x prime is a dummy index. So box of x is equal to box of g f of x prime. But what is box of g? This is box, right?
There is 4-dimensional delta function on the RHS.
Yes.
So like it's non-zero at a single point in time and space.
Yes, absolutely. So this is box, right? So what is box of g? It is I mean, this is the usual way you solve a differential equation, right? Did you understand? So what I have done is that I write the homogeneous part of this equation, and in terms of this new function g, which I will call the Green's function, which is a function of both x and x prime, you can see that psi is equal to the solution psi. This is the solution. So this is a solution to our wave equation, and I have shown that it is a solution because it is constructed like that. This is how you solve. You first solve the homogeneous equation and then you do the particular integral. This is what you get over here. So this is simply this equation split up into these parts, which means that f is your source, right? F is the source. It can be the current or the charge distribution. So it is a known source. So if I solve for g, then I will know psi at any x. So if I am given a source, so this is my universe or space or whatever, I have a localized source at x prime. So let us say it is either rho or j or something like that, and I am asking what is the field which is the A, that is either phi or A, vector A at a point x due to this source, right. So you can see now why this notion of propagator comes. This information about the source is carried by this propagator from the point x prime to the point x and determines what is the solution at the point x. Is this clear? What is the role of this Green's function? Okay.
That is fx dash.
This is fx dash.
Actually, it is bit pixelated. I cannot see the dash.
Yeah, sure. Yeah, this is dash. And once I put in the delta function, this gives me simply f of x, right? Which is my original equation. My original equation is box psi is minus 4 pi f, right? So I have not done anything. I have split up the problem into two parts. I have said I write the homogeneous equation in terms of which the solution psi is given by this, and I have proved it to you in these 3 steps. So how do I find a solution? To find the solution I must solve for g. So how to solve for g? I must solve for equation 1. So the simplest way to solve for equation 1 is to do Fourier transform on both sides. Obviously, I mean both sides. So let us define G of. Okay, now I have to look at my notes because there are 2 pi's all over the place and I don't remember what the 2 pi's are here. So these are the Fourier transform definitions. So G of x prime is equal to, so d4k.
Man, if there is a third order differentiator, so is there any technique like this?
No,
Means this is only valid for second order or first order.
yeah. Who asked this question? Sorry, Ravi. Yeah, I only taught you, right, mathematical physics last year. That's all. You can only teach that because you don't. The rest of it has to be done numerically. Okay, so. Okay, so this is, by the way, just a choice. You could have put 1 by root 2 pi in both, but I am just, since I am following Jackson. By the way, this is from Jackson's famous book on electrodynamics. So I am just keeping the 4 pi's everywhere that he has kept. Okay, sorry, d4k. So these are the, yeah, so I have just put it for the 2 pi power 4 factors. You can split it either way you want, okay, it's your choice. So these are our Fourier transforms. So
In the first equation, there should be also 1 by.
no, that's a choice, it's a choice. This is his choice of delta function. See, delta function, always you have a choice, right? Either you write, let's write in one dimension, delta of x is either 1 by 2 pi dk e to the ikx or minus ikx, whichever way, and then delta k will be dx e to the ikx, okay? Or you can put 1 by root 2 pi on both sides. That's why I said I never remember this, since I didn't want to make those mistakes.
In first equation, G of x prime, in that part, there should be 1 by 2 pi.
No, that because g of k is unknown, you can solve it with whichever way you want, right?
Oh, yeah.
Yeah, it's only for delta function that you have to hurry about that normalization, that's all. G of k is what you need to find out, right? But the k is all 4 momentum. So maybe I can write k as omega comma some c will be there, I don't know where the c is, okay? So now let us write this equation now. So I have box, or I mean maybe because I'm going to do the differentiation, let me keep this del squared. Now g I will write as integral d4k g of k e to the minus I k x minus x prime is equal to minus 4 pi by 2 pi power 4 d4k to the minus I k x minus x prime. Now you can see that this is a function of k, this is a function of k. So this box is going to act only on this term. Is it clear? So what is the first term? What is 1 by c squared d squared by dt squared? So if you want, I can write this as so what is this first term?
Omega square minus omega square.
And the other term is? So now I am going to use k squared as like this. I have plus psi, no?
Yes, ma'am.
Real should be plus sign, plus p square.
Okay. Times I still have the integral, haven't yet done the integral. Oh God. So I can write this as 2 pi squared into 4 pi squared, right? So that is 4 pi cubed d4k e to the minus I k dot x minus x prime. Now you can see that I can just, this is now a function of only k, okay, this is only the x dependence. So on both sides I can just find the coefficients and match the arguments of this integration. So I can equate the integrands. Is this clear? Which means that minus omega squared by c squared plus k squared g of k is equal to minus 1 by 4 pi cubed. Okay?
Yes, ma'am.
So g of k is equal to I'll remove the minus sign and then I'll have 1 by omega squared minus c squared k squared, and then I
And
took,
some of the ma'am, it's not very clearly visible.
this is not visible.
No.
Now
Yes, and now it's better.
is this okay?
Why we have used the mod k?
It is the vector k, no? K squared, 3 vector k.
Yes, ma'am.
Okay, in
Why
fact,
we use the mod?
why we've used a mod? Because it's a, what is mod? It means k dot k, right? Right? I mean it's k dot k, right? The first del brings down the kj and the second del brings down the kj, so it is k dot k, right?
So it is that mod.
Yeah. Yeah, is it okay? Here, del squared let's not call it I, there are too many i's. Is it okay?
Yes, ma'am.
Okay, fine. Yeah, I mean, don't worry about doubts, just ask, okay, because see this, as I said, this class is really a difficulty, you know, that we are all long distance. So don't hesitate to ask. If you have a doubt, just ask, I mean. So okay, here we have some answer here, okay, and this is the solution that we have in Fourier space, and we have to invert it and get the answer in whatever real space, okay. So let's write it down. Where is the answer? G of x prime is equal to integral d4k okay, c squared by 4 pi cubed. So it's d4k g of k e to the minus I k dot x, right? So that's what I'm going to write down. Okay. So you can see that in order to do this integration, I have to worry about this denominator because now I have some zeros, right? Where do I have the zeros?
We have pole.
Yeah, there are 2 poles at plus and minus ck, right? So I have 2 poles at omega is equal to plus or minus ck. And we know how to solve these such integrals with poles. What do you immediately do? You go to the complex plane, right? You go to the complex plane, real omega, im omega, and where are the poles at ck?
We can do epsilon method.
What is epsilon method?
In which we add epsilon term.
Yeah, when once you have to add an I epsilon, no?
Yeah.
But that is complex space, right? So I have to go to complex space, yeah. I have to go to complex space and have here two these things. So now I have to ask some questions now here, sorry, k dot x minus x prime. Okay. So this is what I have as a solution. Now I have to worry about this solution in many different regions. So let us worry about it one by one. Yeah?
Ma'am, when we have written g of x comma x prime as
Yeah.
g of k sub g of k times e to the power minus I k dot x minus x prime.
Yeah.
In writing this, haven't we implicitly assumed that will take the form of x minus x prime instead of x comma x?
Yes. Yes. It's a very good question. It has, but that you can go back and see from here, right? Because the right hand side is a function of x minus x prime alone, the left hand side is also a function of x minus x prime alone. Okay? It's a very good question, yes. I have implicitly assumed that because of the nature of the right hand side, and that is dictated by the solution itself, right? Because when I substitute, this is what I get. By the way, you've done this, I mean this is for the students who didn't do IPHD, you have done this kind of differential equations and their solutions, right?
Yes, sir.
Okay, fine. Okay. So where are we? 1 second. I've kind of lost the flow. Yeah. So we are here. We have to solve this and we have to solve it in many regions. So now let me write explicitly over here this portion as e to the minus I omega t minus t prime times e to the minus I k dot x minus x prime. Okay. Now let me see.
This will add and subtract omega plus ck and omega minus.
Just one moment. I am trying to see if I can drop a lot of constants. So that, okay. Okay, so let us take a physical problem now. I think it will be simplest to do it that way. Let us take one physical problem and say that I had a source over here at t equal to time is equal to t prime. Okay, and sometime later on I want to ask the question, what are the potentials at the point space time point x comma t, right? So we want to solve for psi of x comma t. So I'll solve only one case because I'm not really interested in solving electrodynamics for you. So this, what we will solve here will be called the retarded Green's function, and by analogy you can set up the advanced Green function. So what the retarded Green's function says is that I have a source at a time t prime and I want to ask what is the field at a time t greater than t prime. So after the source has been turned on at a time t prime, what is the solution at a space time point x comma t. So I am going to take this particular solution, okay, just for simplicity, otherwise I will just have to deal with a lot of plus and minus solutions, okay. So what I will do is look at this term over here. If I am saying t is greater than t prime, then this quantity is a positive definite quantity, okay. So I have two ways of closing the contour. Either I can close the contour above like this, or I can close the contour below like this. Is it clear? At the pole we will get to how we will close at the poles, but the closure, the large semicircle that we draw, we have two choices. Now when t is greater than t prime, I am sitting here, suppose I am here on this negative side and I close the contour this way, then your imaginary omega is large and negative, right. So here I will have a part which will look like, the real omega part will oscillate, I am not worried about that, but I have an imaginary omega and I have a positive definite quantity. So let me call it some epsilon which is greater than 0, and minus I into I is, so I have a plus im omega into epsilon, and here im omega is negative and here im omega is positive. Is this clear? So if my epsilon is greater than 0 and I close the contour upwards where im omega is positive, then this simply diverges. So I don't want this. So what I will do is that I will close the contour below. I will close the contour below. Then m omega is negative and large, and this goes to 0 and is well behaved. Is this clear?
Ma'am, so that choice which you have discarded, that will be applicable for advanced.
Yes, exactly. Yeah, that's why I kind of hesitated and I decided that I don't want to solve for both at a time. Okay, because I'll simply go wrong. I mean, I didn't prepare for this, so I just brought my old notes. So I don't want to solve all the possibilities. So you can see that if I choose this contour, then for t greater than t prime, where epsilon is greater than 0, everything is now well defined. Okay, so now I have to do something over here. What will I do at these points? So let me find that. I will now write the contour as, so this is my contour. So this is what, who was, I think Weber was saying, that was Weber's voice, I think, that I put a minus I epsilon for both of them, so that I push these two poles down away from the real axis, or of course I go around the contour like this, so that both the poles are sitting inside this contour and I have to take the contribution of both of them. Okay, so I am now going to solve for this particular contour. Now I know everything will come out right. So what will I have to write? This is second order pole. So c squared. Okay, please forgive me. I am going to now write. I am going to write k without the vectors, vector sign, mod sign, just to speed up things a little. So I want to write this as omega minus ck minus omega plus ck, right? What will I get? So this is omega squared minus c squared k squared. This is omega plus ck minus, minus omega minus ck, right? So this will be 1 by 2 ck. Sorry, I just wrote fractions, okay? I mean, I hope you know how to do this. So this is my solution. So what will be the solution for this? So g will be c squared. I'm just going to do the d omega integration for now. So let me write it as d cubed k, and then I have a 2 ck. Yeah. So I have two poles, one which is omega minus ck and the other which is omega at minus ck, and let me write this term outside, e to the minus I k dot x minus x prime for the 3 vector. So of this part I have taken out the space part and I only have an e to the I omega t minus t prime. So my solution will be omega is ck or omega is minus ck. So I will get e to the minus I ck. So let me call t minus t prime as tau. And then I will have a, because it is 2 pi I times sum over the poles, right? And you can see that this will be, sorry, so this is omega is equal to ck, this is omega is minus ck, so this is sin ck, right? So this, so if I divide this by 2i and I multiply this by 2i, I will get d cubed k by k, some overall factors which I don't care about, e to the I k dot x minus x prime, and then sin ck tau. Up till here is okay? And this I and I becomes minus 1, so there are no I factors. There are lots of c's and pi's and stuff like that. Okay, and I had a, maybe maybe since I am doing this, I will write down the factors once, so that we will write it down here. So g of x prime is equal to here, sorry, c by 2 pi squared d cubed k. I mean, I do not really worry about it, but since you want to look at it, tau, okay, where I have introduced now x minus x prime as r. Okay, now I will write this as O by k, there was a k over there, right? So this is, now I will write this integral as k squared dk d omega k e to the I k r cos theta sin ck tau. This is the usual spherical coordinates. So what do I have here? I have, this is d omega is d cos theta d phi. D phi will simply give me 2 pi. So d cos theta I will write as, so d cos theta e to the I k r cos theta is simply e to the I k r cos theta by I k r from minus 1 to 1, which is e to the I k r minus e to the minus I k r by I k r. So can you see that this is also going to give me a sine? This is going to give me a sine k r. Can you see that this is going to give me a sine k r? So we had a 1 by k from the t integration. I have a 1 by k from the cos theta integration. So both the k's cancel with both the k's. So I do not know this factor anymore, I can look at my notebook. So I have dk only left over. So d cos theta and d phi gives me a 2 pi, I have dropped all the 2 pi's. D cos theta integration gives me a sine k r, and then the other one gave me a sine ck tau. Okay, now what I want you to observe is that this is even function. So I can write this as whatever this quantity was, half of minus infinity to infinity dk sin kr sin ck tau. So x minus x prime is equal to tau r. Okay, and k here, k is equal to, is this okay? Now, and you can see, right, because when I change k to minus k, sine of minus kr is minus sine kr and sine of ck tau is minus sine. So this is even function and therefore I can write it like this. Now you can also see that I can write it like this. So I won't write this is absurd. This is some coefficient minus infinity to infinity dk e to the I ck tau minus kr minus e to the I ck tau plus kr. Okay, so what I have done is that, can you still see this part of the board? Yeah, okay. Sin A, sin B, okay, you can write as e to the I A plus B minus e to the I A minus B. Okay, now you write this as e to the I A plus B is cos A plus B plus I sin A plus B and so on, and you use the formula cos A plus B is cos A cos B plus sin A minus sin A sin B whatever, I think there's a 2 over here, okay, fine. And what you will find is that apart from this, there will be another term which will contain cos A sin B, okay, but that term is odd in this integration and therefore its contribution is 0, and I can write it exactly like this, okay. So what we have done now is that we have done the tau integration, then we did the x theta integration and the phi integration. Now for the k integration, what is this? Can anyone tell me what this is?
Yeah, delta function.
Very nice. So this is the delta function. Since anyway I have dropped all the terms, maybe I should just write the answer down so that when you do the in between steps you will get all the right answers. So you will get answer as one by r, sorry it looks like k, 1 by r delta of tau minus r by c is so what I have done is that I have taken out certain factors. So the coefficient of k here was c tau, right, but I have taken out the c, cancelled various things, and then I get a very simple function like this. So g is this, where this is the vector x minus x prime and tau is the time t minus t prime. So you can see that this tells you a very interesting thing. Where is the source? The source is at a point x prime t prime. Where are you measuring the field? At a point xt. Okay, so this tells you this is t minus t prime minus r by c, or t is equal to t prime plus r by c. What does this mean? The distance between these two is exactly r. That was the vector x minus x prime. And this particle, because this electromagnetic field moves at the velocity of light, which is c. So r by c is the time taken to go from here to here for the disturbance due to the source, the wave front, to travel from here to here, and exactly that much time later, because the source started at t prime plus r by c time later, this quantity is the Green's function at that point. Is this clear? That is why this is a retarded function, and you can see therefore that this quantity is going to be 0, because this is not going to be satisfied at all, because we know that t has to be greater than t prime, and this is not so. Here t will be t prime minus r by c, and therefore it will not be greater than t prime, but this is the one that will contribute in the advanced Green's function. Is it clear? Is it clear?
It is something like misnomer type thing, means we are calling it the retarded Green function, and
This is not normal time. Oh no, no, no. What happens if you do electrostatics? Electrostatics, the potential is instantaneous, right? Suppose I have a charge q, the potential due to this charge q, which is 1 by whatever, if you want 4 pi epsilon naught or whatever, but basically 1 by mod x minus x prime, right? There is no time involved, it's instantaneous.
yeah,
I switch on the source 100,000 kilometers away, instantaneously I feel the potential over here, right? But that's not what is happening here. Now this is the solution after Maxwell wrote his displacement current, and you have proper Lorentz invariant. See, this is, by the way, the problem that happened in the 19th century, 20th century, right? Maxwell's equations were consistent with special theory of relativity automatically. Schrodinger equation was not, right, when in the 1920s when Schrodinger equation was written down. So the question is that should everything satisfy Newton's laws, or should everything satisfy special theory of relativity, or could maybe electrodynamics be different and satisfy special relativity, and Newton's laws need not. So all those confusions were there in the mind of people at that time. So once you write Maxwell's equations, automatically you're getting causality. So this is what you're trying to say, right? I have a causal Green's function, and this is the retarded solution. So G ret. So that means that if I want to write, now I think, so sorry about the sketchy derivation, but I think you can, it's just integrations, okay, and those overall factors you can keep track of. All you have to say now is psi of x is therefore d4 x prime, sorry d4, yeah, x prime, whatever g, let me write it once, x prime, there was a minus 4 pi somewhere, not important, x prime, that is minus 4 pi d4 x prime, and then this is simply delta, so of f of x prime, apart from the other parts, I mean, okay, yeah.
What is definition of retarded and advanced green?
Yeah, so I will tell you. So suppose I say that I write a total psi of x is equal to plus actually let me absorb this 4 pi in the f, okay, I do not want to worry about it, d4 x prime, g of x prime, f of x prime, and I write retarded. So here I have written in. So what we are saying is that I have a source at t prime and localized at x prime. The source is not all over the universe, it is localized in a region around x prime. Then the retarded Green's function is exactly that which will propagate from the source to the point at which we need to measure the potential, okay, and it does it in a causal time t minus t prime is equal to r by c. Is this clear? So it tells you that once the source has been switched on, at a time t is equal to that time t prime plus r by c later, I can tell you what will be the potential at the new point, which is a distance capital R away from it at a later time. So this is the retarded Green's function, because it takes that much time for the disturbance from the source at x prime to reach the point at which we are going to measure it, okay. Now suppose instead of closing the contour this way, I had instead closed the contour like this and asked for all solutions t less than t prime, okay, then I would have got in exactly the same way the advanced Green function. It will be the other delta function, you can write that down, you can solve exactly the same way, you will get the other Green's function. What this tells you is that some source has turned on and then let us say that it got switched off. After the source switches off, and there must be no more disturbance at the source, okay, let us say. So what was psi n is simply some boundary condition, okay. This could have been 0, maybe let us say that there were no charges anywhere. So let us say that, let us talk about electrostatics. So the electric potential is 0 everywhere, and then once the source is turned on, you get this much contribution and you get a non-zero potential. Now it is the other way around, you have switched off your source. You must ensure that after switching off the source, no more field is left over there, right. That means if you go backwards in time by the amount of time taken to traverse from here to here, once that field is switched off, you must have no more field at that point. So psi out, psi will now be whatever, maybe psi out will be 0, non-zero, plus G advanced times f times d4x. Is this clear? So the last statement I want, yeah. I will repeat it after I complete what is Feynman propagator. Then you will try to see the relationship between the two. So I hope you realize that both G retarded and G advanced are causal Green's functions. So G retarded tells you that so far back in time you had a source due to which you had a disturbance, and the G advanced tells you that you had to have a source at least by that time, so that in future you can see at up till some time t, you can see that there was a non-zero field. Now I come to the Feynman propagator. Of course, you can write it down now for Klein-Gordon equation, but all your propagators will look identical, and in the Feynman propagator, the way you take the contour is like this. Okay, so you include one or exclude one, and on either side you can see that one will contribute on either side, whether I close the contour from this side or close the contour from that side. This is the meaning of the Feynman propagator. I just want to make two remarks, then we will come back to this. Okay, so you can see that the origin comes from the same set of poles. It depends on which one you take into account. The first thing is that the Feynman propagator, so let me call it Fp, is not causal, and this we already saw, right? The fact that the mediator is not on shell, it's not actually communicating any information, because if something is not on shell, see, this is like faster than light, right? If something travels faster than light, that means it's off shell, then I can get information faster than light, but this is not possible. So all these virtual propagators are not actually conveying any information at all. Although they have support outside the light cone, there is no information being conveyed by that particle. The second thing is that the way the Feynman propagator is, you remember that how did we get this? We wrote e to the minus I omega t minus t prime, and we solved the retarded Green's function when t was greater than t prime. We solved the advanced Green function when t was less than t prime. We did not solve it, but that is how you will solve it. Okay. Now what happens is that the Feynman propagator, it propagates the positive energy solutions as going forwards in time, that is t is larger than the t prime where it was produced, and the negative energy solutions backwards in time. So we are now coming across something very new. This is the physical interpretation. As I said, the formal definition, by the way, so the Feynman propagator or the Green's function is actually the 2-point a mu of x, a nu of y, time ordered. You learn what is time ordered, and a vacuum expectation value of that. Okay, so this is something you will learn in the field theory. Don't worry about what the definition is. This is the definition that we are going to use. Okay, we have a propagator. So what we are saying is this: everything depends on this. Now we know that, for example, in Dirac equation, you have positive energy states and negative energy states. So if you have positive energy states, okay, then it's meaningful to look at t greater than t prime, and then you close the contour here, everything is well defined. For negative energy states, omega is less than 0, so there's an extra minus sign. So you take t less than t prime, you close the contour from above, and what do you mean by t less than t prime? You are saying that you are going earlier and earlier times before the source in some sense, and therefore you say that it's something like saying your antiparticles are going backwards in time, your particles are going forwards in time, but that is not really the correct description. In field theory, you don't have to worry about going backwards or forwards in time. These are the possible solutions that you have. It is not causal, but once you calculate everything, your entire matrix element will not violate causality, everything will simply go through correctly. Is this clear? Is this okay? Can you see that there is a relationship between this kind of propagator and this, and that is why it is also propagating something. It is propagating some information, but here it is propagating all the energy states because there are only positive energy states classically. Here it is actually doing something different because Your quantum field theory has both positive and negative energy states. Okay.
And
Yeah.
as you were saying, it propagate information,
Yes.
right? But
Yes.
it is not causal. So how can it propagate information?
Yeah, that is the whole point, right? Because it's propagating information in two different ways, that's all. So if I separate out the positive and negative energy solutions, then of course everything behaves very nicely. That's what we will do, right? Because we will put particle and antiparticle on an equal footing, and when we talk about electron muon scattering or we talk about positron anti-muon scattering, we will apply the appropriate thing and everything will be fine. Okay?
How it is not causal? I don't understand.
See, because, okay, fine. Now you're, how is it not causal? Because it has, the simplest way is to go back to what we talked about, that this propagator is not on shell. What do you mean by causal? If I say that p squared is equal to m squared, then if I'm going, if this object p with momentum p or energy E is travelling from a point x1 to a point x2, I mean, so then t1 and t2, then it can only reach maximum, the fastest it can travel depends on the energy mass relationship. So I can calculate everything given p, right? So I know E squared is p squared plus m squared, then I can calculate its velocity, okay, and therefore I can find out the time it will take to reach t2 from t1. That is causal. So causal behavior, what can I take off? I'll take this off. Causal behavior means that this is my time and this is all my space, this is my light cone, right? So if I have a massless particle, then the massless particle travels at x is equal to t, I mean, okay, x is equal to ct, and anything which is more massive will travel like this, right?
Yes.
This is causality. Now what does it mean? This is because we have always satisfying this 4 vector solution x mu, which is c squared t squared minus x squared y squared z squared is equal to constant, right? And therefore also we are satisfying, because the same, in the same space I have the vector p mu is equal to p0 squared minus equal to constant, right? But for a propagator, that's why I said the simplest way is to look at the propagator. This is not a constant. This is not the m squared, because it's a virtual object. So it can even go here, it can go here, okay, or it can even go, I mean, see, it can be either time-like or space-like, right? So both of the things are available to it. I mean, that's what we saw last time, right? It can be either q squared less than 0 is space-like, q squared greater than 0 is time-like. So I can violate this light cone. So anything is outside the light cone is not causal, right? But that's what I said, that what happens is that it is only a propagator, it is not a physically observable particle. At some point that's going to get absorbed by something else, and then you're going to see a physical particle, which is your PC and your PD in your A plus B goes to C plus D. And these two are physical particles, they will be on shell and everything will be causal. So the process as a whole will be causal, but your intermediate propagator is not going to actually do that for you, okay? But basically the Feynman propagator understands that in quantum mechanics now I will have both positive and negative energy solutions, and it propagates them appropriately, because what does Schrodinger do? Schrodinger always propagates states as e to the minus IET, right? It's always causal, always energy greater than 0. But here we don't have that, right? So I don't have e to the minus I omega t, I have both possibilities. I have either t greater than or less than t prime, and I have either omega greater than or less than 0. So both advanced and retarded Green's functions are completely classical and causal, okay? I can write my solution depending on the boundary condition. If I am given initial conditions, I will use retarded Green's function. If I am given final boundary condition, I will use advanced Green function, but they are both completely causal. Okay, it's a matter of convenience depending on the problem which one I use. But in this case, it's not like that. Here what I say is that if omega is greater than 0, I will use the retarded Green's function. If omega is less than 0, I will use the advanced Green's function. So I will use different solutions depending on what is the nature of the particle that I have. Is it clear? So that's all I want. So I have not derived, please understand, I have shown you that, by the way, I have shown you that the propagator looks like 1 by, so if you remember in K space, my g of k, small g of k, I should have was 1 by, apart from some constants, by k minus k squared, which is actually 1 by k squared, 4 vector k squared. Okay. What have I got for Feynman propagator? I have also got minus 1 by k q squared. So they look the same. Okay, but the physical interpretation of them is different. So this 1 by k squared in k space being the propagator is the same for classical electrodynamics as well as quantum electrodynamics. Okay.
Ma'am, we can write Feynman propagator in the combination of these causal advanced and retarded.
Yeah.
Right?
So basically,
Ma'am, Krishna is out of the class. He lost the connection.
oh, okay. Is he trying to join back in?
Yeah.
Okay, fine. Okay. So maybe I'll just stop by writing these 3 equations here.
Ma'am, you are the host, so you have to accept it.
No, I made Prabhat the host.
But no, you are not the host.
Oh.
You left.
No, actually, I am not the host right now.
Okay, fine, no problem. Okay. And I said, don't worry too much about this because you will be doing this in your quantum field theory course. And moreover, it's a Lorentz invariant quantity. Okay. So these are all the remarks I wanted to make. As I said, the technology that we need to actually derive this starting from field theory we don't have. I have tried to motivate for you starting from classical electrodynamics and try to make a kind of a loose analogy between Feynman propagator and the advanced and retarded Green's functions of electrodynamics. I hope that didn't confuse you further, but basically, as I said, the key thing that we will understand in words is that it takes into account the fact that there are both positive and negative energy solutions, and the fact that it corresponds to propagators which are off shell. Okay, is it clear? In fact, you will find that this will be the propagator for several particles. You just have to put, instead of, sorry, k squared by n plus I epsilon, sorry, no mass. So this will be the propagator for several particles, especially scalar fields will look like this, and when we come to Dirac equation it will look a little different, okay. So I will stop here now, and I wanted to try to complete that cross section calculation, but we will do it in the next class, okay. Is it okay? As I said, don't worry if you didn't understand this derivation. Of course, you should be able to derive G retarded and G advanced for classical electrodynamics. It should be there in any textbook. It's in Zuber or Jackson, anywhere it should be there, not a problem. And but this, as I said, I have simply written down by analogy. I have not derived it, and it will be derived for you in the other class. Okay?
Ma'am, using Feynman propagator, we can propagate in space-like distances, right?
Yes, yes. Space-like, time-like, anything, right? That is the whole point of the propagator. Okay, it is off-shell. It is off-shell. It can be off-shell in any way possible.
So, ma'am, as virtual particles are not causal.
Yes, they are not. They are not causal. That's the whole point, right?
So they can be absorbed before even they are emitted.
Yes, you don't even ask that question, okay? See, that's the whole point. Delta E, delta T must be greater than or equal to H cross, okay? You don't ask anything more than that. What do you mean by absorbed before they are emitted? Then they are like antiparticles, right? So the thing is that when we write, you will write something called the mode expansion for fields, and you will understand that psi, even though the expressions look very similar, what you call the wave function psi will be made up of two parts. One is the so-called particle aspect and the other is the antiparticle aspect. And the whole thing is one wave function. So you are not going to ask is it a particle or an antiparticle at all, because that wave function codes for both. That is why the propagator also codes for both. Is it clear? And what you think of as actually being absorbed before it was emitted is actually then you are talking about antiparticles, because the way to look at it then is to say that if AB goes to CD, this is the last statement, I don't want to, yeah, AB goes to CD is the same as C bar D bar goes to A bar B bar. Okay, so the final state particle becomes initial state antiparticle and vice versa. Okay, that's what you mean by going backwards in time. Okay. Okay, very good. So I'll stop here. As I said, this is simply hand waving. All we are going to do concretely is use the expressions that I have given for the propagator and vertex and actually calculate the matrix element and therefore the cross section. Okay, we'll stop over here. Thank you.